Okay, good morning, lads and ladies. Welcome back. Ooh, a little crazy this morning. Today we are going to finish talking about rational functions. Specifically, we're going to talk about rational and polynomial inequalities. So last time we kind of introduced this and we saw some of the follies, little traps that we can fall into if we treat these inequalities the way we treat linear inequalities or equations. I outlined a little bit the process that we're going to use to solve them. So today I just want to get a little bit more practice with that process, kind of give you a feel for how these things go, and give you some examples that we can work through so you can kind of use them as prototypes as you study for the test and work homework problems. Just a quick reminder that our test is going to be next Monday. That is exam 2. So hair tie just broke. So let me find another one. I'll be right back. All right. So yeah, so quick reminder, our test is going to be next Monday. Okay. All right. Yeah, so that's it. Today we're talking about rational inequalities. This is our last lecture before the second test. Second test is on Monday. So let's do it. Let's take a look at some of these things. Turn on the document camera here and we can get moving. Cool. MAC 1140 section O, which is pre-calculus. Today is the 20th of October, 2021. Today, polynomial rational inequalities. And that's section 3.7. The procedure for solving inequalities like these is pretty straightforward, but you got to follow it. So last time we looked at the 1 over x is less than 0 inequality, and we saw why we cannot do the sort of naive thing there and try to solve for x. The general gist of that was that you can't multiply on both sides of an inequality by a variable. And in general, when you're dealing with inequalities that are nonlinear, you need to be very careful to not do things that would change the solution set. So the sort of stuff that would change the solution set for an inequality like that is multiplying both sides by any variable quantity, canceling variable factors, that sort of thing. So the stuff that is safe, the procedure that we outlined, procedure to solve rational inequalities. First, we pull everything to one side. Making the other side 0. Then we, if necessary, have a common denominator. If you're looking at a polynomial inequality, then there aren't any denominators, so you don't need to worry about having a common denominator. But if there are fractions, you need to have a common denominator. and combine like terms. Right, and I think it's this second step that is actually the most challenging algebra-wise, because sometimes this means adding up two big fractions, all with lots of polynomial stuff top and bottom. So you need to be quite careful as you do that. Your third step is going to be to factor everything. And then your book has a special term. So the numbers that would be the roots from those factors, your book calls cut points. So record the cut points where either the top equals 0 or the bottom equals 0. And then, just like we did at the start of the semester when we solved these sort of inequalities in section 1.8, you're going to make a number line. With those cut points. The cut points plotted on the number line. We'll split that line up into several regions. And then you're going to determine the sign in each region. And there's a bunch of ways you can do this. You can do this with test points. You can do this by knowing one sign and then using multiplicities. There's lots and lots of ways to do this. So I'll just make a little comment here. Use multiplicities. I'll just leave it at that. You can also use end behavior, horizontal asymptotes, y-intercept. Any of those can be helpful to get you the first sign. And then once you have the first sign or a sign in any one of those regions, you can use multiplicities to get the rest. Let's start with an example of a polynomial inequality, and then we'll build up to some more complicated rational inequalities. So yeah, let's do it. Let's solve the inequality. 2x cubed plus x squared plus 6 is greater than or equal to 13x. So the object on the left and the right-hand side are both polynomials. Remember, polynomials are included in the set of all rational functions. So really the procedure for rational inequality and polynomial inequalities are the same, just that with a polynomial inequality, you don't have to have a common denominator because there are no denominators. So the very first thing I should do is pull everything to one side. That'll give me 2x cubed plus x squared minus 13x plus 6 is greater than or equal to 0. I've subtracted 13x from both sides. Now I need to factor this. Factoring this can be a bit of work. At a glance, I don't think this is going to factor by grouping, even though it has 4 terms and could maybe be factored by grouping. If I pull out the x squared from here, I won't have this left over. And these two don't have any common factors. I can pull out 13's prime. So we're going to need our rational roots down. So we write down our list of p's and q's. P's are divisors of 6. So that's 6, 3, 2, and 1. Q is 2. So 2's divisors are just 2 and 1. And then we're going to start trying to figure out our possible rational roots. That's that list. So we'd have plus and minus 6, plus minus 3, plus minus 2, plus minus 1, and then plus minus 6 over 2, which is 3. So that's already on the list. I won't write it. Plus minus 3 over 2. Plus minus 2 over 2 is 1. That's already on the list. Plus minus 1 over 2. So this is my list of possible rational roots for this polynomial that I'm trying to factor. And I'm going to save us some time here because I worked this out earlier. 2 is a root. So if I perform the synthetic division, testing the root 2, that means I write the root and then I write the coefficients here, which are 2, 1, negative 13, and positive 6. 2, 1, negative 13, 6, yeah. And then we go ahead and do that synthetic division. Bring down the 2. That product is 4. That sum is 5. That product is 10. That sum is negative 3. That product is negative 6. And that sum is 0. So what do I learn here? My polynomial is x minus 2 times 2x squared plus 5x minus 3. So all of that is greater than or equal to 0. And then we still have to factor this quadratic, 2x squared plus 5x minus 3. So my AC method is the thing that comes to the rescue here. 2 times negative 3 is negative 6. I need two numbers that multiply to negative 6 and add up to positive 5. Those are going to be positive 6 and negative 1. So this is 2x squared plus 6x minus x minus 3. Then I factor this by grouping. And I get 2x minus 1 times x plus 3. So the fully factored form of this polynomial is x minus 2 times 2x minus 1 times x plus 3. And we have that is greater than or equal to 0. So we pulled everything to one side. That was step 1. There weren't any fractions to combine with the common denominator, so we didn't have to do any of that. Then we factored everything. We need to write down these cut points, the places where this polynomial or this function here can change sign. Those come from these factors. So it's 2, 1/2, and negative 3. And then we'll plot those on a number. So negative 3, positive 1/2, positive 2. And this chops the number line up into several regions. Now this should look familiar, right? This is what we did at the beginning of the semester. I gave you inequalities in this form, right? Where things were already pulled to one side and already factored. And then you had to create this number line, or if you followed the textbook, you created a sign chart. And you tested a point from each of these regions. So I've got 1, 2, 3, 4 regions. And you could plug in a point from each of those regions to check whether this inequality is true or not in those regions. But that takes a lot of time. That takes a lot of time, and we don't want to do that. It would be really nice if we had some way to do this faster. And the good news is that now that we've studied polynomials and rational functions, we do know how to do this faster. Can anybody tell me the sign of this function? Right, looking at it up here, of course, it's the same as these, but can anybody tell me whether this function is positive or negative to the left of negative 3? Think about the end behavior.
It's going to approach negative infinity on the x-axis as it approaches negative infinity on the y-axis.
Yeah. So the normal way we'd say this end behavior is as x goes to negative infinity, y also goes to negative infinity. So as I run very far off to the left, my graph is pointing down, right? This polynomial right here has an arrow pointing down on the left and up on the right. That arrow down on the left means that we got to be negative over here. Remember, in each one of these regions, this function stays positive or stays negative. So if when we go really far out here, we know that the thing is going down towards negative infinity, that means everywhere in here, the function has to be negative. The purpose of these cut points, these are the only places where this thing can change sign, go from negative to positive or positive to negative. This is coming from the end behavior. We could also fill in the far right one from the end behavior if we wanted to. We know that this one will be positive. So x goes to positive infinity, y goes to positive infinity. Because this is a polynomial of odd degree, degree 3, with a positive lead coefficient. I still need to know whether this is a positive or a negative, whether this is a positive or a negative, and that's where the multiplicities come in. So this -3, this cut point -3 is coming from this factor, which is a multiplicity 1 factor. Right? Since 1 is odd, that means we will change sign as we jump over him. This 1/2 is coming from this factor, which is an odd multiplicity factor. Right? It's multiplicity 1. So again, we will change sign as we jump over this guy. And we can use multiplicities to check this also, right? This guy, 2, is coming from this factor, which is an odd multiplicity factor. So I should change sign as I jump over him, and we do. So once you have this number line complete, you're done. We wanted to answer, where is this inequality true? For what x values is this inequality true? And that's equivalent to saying, for what x values is this inequality true? So I'm looking for places where this function, whose signs I've just written down here, is greater than or equal to 0. So I'm looking for places where that function is positive. Well, that's here and here. So from -3 to 1/2 and from 2 to infinity. The only thing we have to be careful about is the endpoints. Infinity always gets a parentheses. This is a greater than or equal to 0. And at each of these numbers, -3, 1/2, and 2, this function is equal to 0, right? Those are the roots. So if you plug 2 in here, you get 0 is greater than or equal to 0, right? This factor would be 0. I don't care what these are, because when you multiply by 0, you get 0. So when you plug 2 in here, the left-hand side, this piece, will all be 0. And you get the statement 0 is greater than or equal to 0, which is a true statement. So we include 2 in our solution set. And by the exact same logic, you need to include both 1/2 and -3. If you plug 1/2 in here, then this middle factor is 0, which makes everything here 0. And 0 is greater than or equal to 0. So we use a bracket here. And the same is true with -3, bracket there. So that's it. You see how using end behavior and multiplicity speeds this up compared to what we did at the start of the semester, where you had to test a point from each region. It really does. The other difference between this problem and the problems we solved at the beginning of the semester is that now you know how to factor these sort of things. So I can give it to you in this expanded form, and you have to put it together into this factored form. Any questions on what we did here? So kind of strategically, what we need after you have your cut points, what you need is the sign in any one of these regions and the multiplicities. You can get the sign in one of those regions from the end behavior. Sometimes we get it from the y-intercept if the end behavior doesn't help. Other times you may have to just test one point. But you should never have to test more than 1 point. It's a big time saver. All right, let's try one more. This time, let's have it be a rational function. Okay, this time I want you guys to tell me what to do. So what's my first step?
Move the one over.
Sorry, can you say that just one more time?
Move the one over.
Yeah, we got to pull this one over here, right? We need to make one of those sides the 0. So my first step is to subtract this one over. So I'll have 1 minus 2x over x squared minus 2x minus 3. Minus 1 is greater than or equal to 0. The trick to not messing up this algebra is to not try to do too much at once. Just do one thing at a time. So we subtracted the 1 over. What do we do now?
Get rid of the bottom or create a common denominator.
Yeah, exactly. I've got two different pieces here. One of them has this denominator. The other one has denominator 1. So if I'm going to write those as a single fraction, I need to have a common denominator. And that's our step 2. Now, in order to put these together with a common denominator, I need to multiply this negative 1 by x squared minus 2x minus 3 over x squared minus 2x minus 3. So I'll have 1 minus 2x over x squared minus 2x minus 3 minus x squared minus 2x minus 3 over x squared minus 2x minus 3. And all of that is still greater than or equal to 0. Now that I've got these guys written with the same denominator, I can subtract the fractions by subtracting the numerators. And remember, the top and bottom of fractions always in parentheses. So when you subtract, you need to distribute this negative upstairs. So you'll have 1 minus 2x minus x squared plus 2x plus 3 over x squared minus 2x minus 3 greater than or equal to 0. Now I'm going to combine my like terms in the numerator. I'm doing that so I can factor. So I've got an x squared here, it's negative. I've got a minus 2x here and a plus 2x here, those go away. I've got a plus 1 and a plus 3, so that's plus 4. This is over x squared minus 2x minus 3. And all of that is still greater than or equal to 0. Okay, what's next?
Factor the top and bottom.
Very, very good. So now we're going to factor the top and bottom. I would make it maybe off to the side here. Negative x squared plus 4 is the same as 4 minus x squared. So I can factor him as a difference of squares. Like this. And the bottom, x squared minus 2x minus 3, how does he factor? Did I lose you guys?
-3 and +1.
Very good, very good. Are we all comfortable with this trick here? Things got a little quiet there.
Yeah.
All right, so if I'm adding like -9 to 4, that's the same as having 4 and subtracting 9. So writing it this way just makes it easier to see the difference of squares. And then, yeah, this one factors very nicely as x minus 3 times x plus 1. So now my third step here, 2 minus x times 2 plus x over x minus 3 times x plus 1. Still wanting to know where this is greater than or equal to 0. My cut points are any number where any of these factors is 0, right? What they really are the x-intercepts and vertical asymptotes. We saw over the last few classes that the places where a rational function can change sign are where it crosses the x-axis or as you go over a vertical asymptote. So those cut points are places where the top is 0 or the bottom is 0. X-intercepts, vertical asymptotes. Those are -2, -1, +2, and +3 from these. So we're going to plot those on a number line. There we go. And this splits my number line up into several regions. Oops. All right. I need to find the sign in one of these regions in order to use my multiplicity trick to get the sign in the rest of them. Can anybody tell me the sign of this function in the leftmost region?
Is it negative again?
It is. Yeah, it is negative. That's wonderful. Why?
The polynomial is to the degree 2, so it looks kind of like a parabola.
Well, I would be careful here. So the function in question this time is not a polynomial, right? The top and bottom are both polynomials, but that means the whole thing is a rational function. So the end behavior here is different from polynomial end behavior. What is the analogous concept of end behavior for a rational function? Like as we get really, really, really far away from 0, what sort of feature of the graph are we talking about when we're talking about a rational function? Which one of those like 5 things that we like to find are we talking about for end behavior? You're correct that it's negative. I'm just trying to make sure we're all on the same page and can see why. What is the horizontal asymptote for this function? So the end behavior for a rational function is the horizontal asymptote, right? That's what the function does as you get really, really far away from zero. It tries to settle down on that horizontal asymptote. So if I look at this step, I think that's where it's easiest to see what the HA is.
-1.
Yeah, very good. The degree of the top is 2, the degree of the bottom is 2. Since those match, we take the ratio of lead coefficients. So the horizontal asymptote here is the line y equals -1. So as you get really, really far to the left, thinking about the graph of this function, as you run way out this way, this expression is very, very close to -1. In particular, it's negative. And now, since each of these factors is a multiplicity 1 factor, we will change sign as we hop from region to region. So the next region would be positive, and then the region after that would be negative, and the region after that would be positive, and so on. And we could have argued the same sort of thing over here, right? That because the horizontal asymptote is the line y equals -1, that when you plug in really big x's, you're going to get something very close to -1 out. In particular, it's negative. So we've completed the sign chart, our number line here. We know where this function is positive and where it is negative. We have to be a little bit more careful when it comes to writing down the answer this time, because not every cut point will be a part of the answer. Some of these cut points, the ones that come from the bottom, we cannot plug into this expression because it makes the whole thing undefined. So the solution set we're looking for greater than or equal to 0, so that's positive. So we're looking for -2 to -1, unioned with 2 to 3. And some of these we can include, some of them we cannot. Which can we include?
Wait, could you repeat that again?
So I'm trying to figure out whether to put brackets or parentheses on this interval, and brackets or parentheses on this interval. To that end, I need to know if I plug in -2, does this become a true statement or not? When I plug in -1, is this a true statement or not? And so on.
So we can't use the ones on the bottom, which would be 3 and -1, because that would make it undefined.
Perfect. Did everybody hear that? That was perfect. So like Shauna was saying, if you try to plug -1 into this expression, you get something up here and you get 0 down here, right? When you plug in -1, this factor is 0, which makes the whole bottom 0. So when you plug in -1, this whole apparatus here is undefined. So you cannot include -1 in your solution set. What about -2? What happens if we plug -2 in here?
It'll make the top 0.
Yeah, this factor would be 0. Up here, we'd have like 4 times 0, which is 0. And down here, we would have -5 times -1. So you'd have 0 over 5. 0 over 5 is equal to 0. And 0 is greater than or equal to 0. So I can include the -2. And we continue with the same logic to test these guys. So if I plug in +2, this piece will be 0, right? The top would be 0 times 4, which is 0. The bottom would be -1 times 3, which is -3. So you'd have 0 over -3, which is 0. And again, 0 is greater than or equal to 0. So we can include the 2. And if you try to plug 3 into this thing, the downstairs is 0. So we cannot include him. So this is my solution set. The moral of the story here is if you're dealing with a greater than or equal to, or a less than or equal to, what we call weak inequalities, instead of strictly greater than, you've got greater than or equal to. You need to check and see whether the endpoints of your solution set satisfy the inequality. And the sort of fast way to get there is what I think Shauna said. If the endpoint came from the downstairs here, then you cannot include it because that will make the bottom 0. If the endpoint came from the upstairs here, then you can include it because that will make the top and hence the whole fraction 0. All right, so this is our solution step. Just like graphing rational functions, I promise you there will be a problem on the test like that. I promise you there will be a problem on the test like this, where I give you a rational inequality and you have to run through these steps. So are there any questions on what we did here, why we did it, why it came out this way?
I have a question.
Yeah, Joyce, what's up?
I was wondering, when you found out like whether it was positive or negative, why did you just alternate them?
Because each of these factors is a multiplicity 1 factor. So remember, if you have an odd multiplicity, you will change sign as you jump over that number.
Okay.
So that's really it. All of these were odd multiplicity factors. So every time I jump over one of these, we're going to change sign. Let me see if I can find one where we have some other multiplicity stuff going on. No, we'll not do that one. That's the same shit. No, let's not do it graphically. Let me dig in here, see if we can find one of these. Man, your book is really short on examples like these. I'm trying to find something in the problem set here. There really aren't many. Okay. How about this? Let's solve the inequality. Oh, so there it is. So this guy, they've already done the bulk of the work for us, pulling everything to one side, having a common denominator, putting everything together, factoring top and bottom. That's already been done. So what we do is we write down the cut points. From the bottom, I have -2 and -1. And from the top, I have 1. Okay. And those will chop up my number line into 3 regions, 4 regions. Sorry. Again, I need to know one of these to get started, and then I can use my multiplicity trick. So I think it might be worthwhile to note that x minus 1 squared over x plus 1 times x plus 2 is the same as x squared minus 2x plus 1 over x squared plus 3x plus 2. So can anybody tell me the sign of that function in this far left region?
Positive.
Very good. Very good. We have to be positive over here. Why? Well, what's the horizontal asymptote?
1.
Yeah, it's the line y equals 1. So this function gets really, really close to outputting the number 1 as x goes way off to the left. In particular, it's got to be positive, right? Because 1 is positive. Now, as we hop over -2, what happens? Does it stay positive or become negative?
It changes sign.
Changes sign, right? Because the x plus 2 factor here is an odd multiplicity. It's a multiplicity 1. So we'll go from positive to negative. And again, as we hop over the -1, that comes from this factor. We will change sign because that's also a multiplicity 1 factor. But then as we hop over the positive 1 comes from this factor, which is multiplicity 2. So because that's an even multiplicity factor, we will not change sign. All right, so that's how the multiplicities can save us a lot of time. We don't always just alternate sign. It has to do with the multiplicity of the factor. Are we all comfy with why we didn't change sign coming over here, why we stayed positive?
No, I don't understand.
So let me note the multiplicities for each of these. This is multiplicity 1. This is multiplicity 1. This is multiplicity 2. So remember, as you jump over a vertical asymptote or x-intercept, whether you change sign or not depends on the multiplicity of the factor from which that feature comes. So both of these vertical asymptotes, -2 and -1, are multiplicity 1. They're both odd multiplicity. So we change sign as we jump over the -2, and we change sign as we jump over the -1. The positive 1, that cut point comes from this guy, which is a multiplicity 2 factor. Because that multiplicity is even, we will not change sign. So if this was a negative, this would be negative. Since this is positive, this is going to be positive as well.
If we had another number outside of that one, would the next one be negative still?
Another number, what do we mean exactly?
Like if we kept going positive on the number line, if we had a 2 after that as another cut point, would it continue to flip-flop again? Would it be negative for the next one? And it's only positive there because of the numerator.
It depends on the multiplicity. So if we had, it's a good question. Let's see. So if I also had like if I had just a regular x minus 2 here, that would give me a 2 here. And since this is, as it's written right now, multiplicity 1, we would change sign. If this was an x minus 2 squared, then we would still be a plus here. All right, let's do one more like this. Let me throw us. Let's do something like this. How about x plus 3 squared times x minus 1 over x cubed times x plus 1 squared. It's less than 0. Real quick, before I go off to this next example, let me just write down the answer for the purple question here. So I'm going to scratch this, because the problem we were originally solving is just this. We want to know where is this function strictly positive. So that would be from -1 to 1 and from 1 to 2, from 1 to infinity. I don't include any endpoints because this is a strict inequality. So the solution set to the original problem here is this. Because we're strictly positive from -1 to 1 and from 1 to infinity. So let's look at this guy. Now I've got other stuff of different multiplicities. My cut points here. I've got -3 from this guy. -1 from this guy. 0 from this guy. And 1 from this guy. And let's record each of their multiplicities. The -3 coming from this factor is multiplicity 2. The -1 coming from this guy is also multiplicity 2. The 0 coming from this guy is multiplicity 3. And the 1 coming from this guy is multiplicity 1. Are we comfortable with where these multiplicities are coming from? Remember, the multiplicity is just the power of the factor. Okay, so here's my number line. The degree of the top here is 3. The degree of the bottom here is 5. So the horizontal asymptote is the line y = 0, which is neither positive nor negative. So the horizontal asymptote will not save me here. Also, the y-intercept, there is no y-intercept because the function is undefined at x = 0. So in this case, we are going to have to test at least one point. Let me test a point over here. Let's test x = 2. If I plug 2, which is in this region, into this apparatus, I get 2 + 3 all squared, which is 5 squared, times 2 - 1 is 1, divided by 2 cubed, which is, I'll just write it as 2 cubed for now, times 2 + 1 all squared, which is 3 squared. So that every piece here is positive, right? This is, the top is 25, the bottom is 8 times 9 is 72, which is positive. So we're positive here. Now, as I jump over the 1, am I going to change sign or not? Will I stay positive here like I am over here, or will I flip to being negative? Remember, it has to do with whether the multiplicity is even or odd. So what is the multiplicity of the factor that gave me this 1?
1.
1, right? And 1, that multiplicity is odd. 1's an odd number. So as I jump over this, am I going to change sign to become negative, or am I going to stay the same sign, positive?
Aren't you gonna change the sign because it's negative, like it changed?
I am going to change sign. The reason is because this is an odd multiplicity. All right, so odd multiplicity. Means you're going to change sign. Even multiplicity means we don't change sign. That's what's going on, right? So this guy is an odd multiplicity. He's coming from this multiplicity 1 factor. So as I jump over him, I must change sign. This is a multiplicity 1 thing. The 0, that's a multiplicity 3 thing, right? He came from the factor x cubed. So as I jump over this guy, will I change sign from negative to positive, or will I stay the same sign?
Change sign.
Change sign, right? Because it's an odd multiplicity. So since I know I'm negative over here, and I know when I hop over this, I need to change sign, we're going to be positive in here. All right, what about the negative 1? What is his
You don't change it.
Yeah, so he's multiplicity 2, right? The negative 1 is coming from this factor, which is multiplicity 2. So since I'm positive over here, and even multiplicities, we don't change sign, we're going to stay positive. And the negative 3, his multiplicity is also 2. So as
Oh, so you don't change it either.
very good, very good. So we're feeling a little better about this multiplicity business?
Yes.
Very good, very good. All right, now let's write down the solution to this inequality. I'm asking, where is this apparatus less than 0? So I'm asking, where is this function negative? There's only one region. And since it's a strict inequality, I know I'm not going to include the endpoints no matter where they come from. So my solution set is the open interval from 0 to 1. Okay, so it's not too bad. It's not too bad. And if you get stuck or if you're uncertain, you can always test a point. If I don't know, if for whatever reason I'm doubting that this should be positive, this just looks weird to me to have 3 positives in a row, I could plug negative 2 in here, right? Inside this region from negative 3 to negative 1 is the number negative 2. So I could test negative 2 the same way I tested positive 2 out here and verify that this thing is indeed positive in this region. When you plug negative 2 in here, you're going to get a positive number out. It's not too bad. So once you're comfortable with this multiplicity business, I think the bulk of the work for these problems is the algebra to get them into this form, right? This can actually be quite a bit of a headache just to get here. So what I would like to do is get us just a teensy bit more practice with that. Let's try something that usually throws people for a loop. So how about?
I have a question.
Sure.
Would this be similar to how, like, on a number line, you put a dotted line and an undotted line? Like one is shaded, one is like solid.
It sounds like you're thinking maybe of linear inequalities, like systems of linear inequalities, where you're like shading a region in the XY plane, and then you use either a dotted line or a solid line, depending on whether the points on that line are a part of the solution. Is that what you're thinking of?
I think that is where I think we already went over it earlier this semester, to where you put like a shaded dot on one point and then a unshaded dot on the other, to where you just see if it's
yes. So if I wanted to graph this solution set, yes, that is the same thing. So if I wanted to graph this solution set, like, and 0 is here, 1 is here, we know everything in between is a part of the solution set. And then there's sort of 2 notations for that, right? You can use these parentheses here to indicate that the endpoints are not a part of the solution set. Or if 0 is here and 1 is here, you could put like an open circle here, and an open circle here. So these would be the 2 different ways you could graph this solution set on the number line. And yeah, that is the parentheses versus brackets thing here is the same as the open versus closed thing here. Okay, let's look at one more. I think we've got time for one more, right? Yeah. And let's make it a weak inequality, so we have to deal with the endpoints. And let's also make it one where there's some algebra to do. Let's solve 6 over x minus 1 minus 6 over x is greater than or equal to 1. So before I can get to my cut points and number line stuff, I need to pull everything to one side, put it all together in one fraction, combine like terms, and factor the top and bottom. So my first step is to pull everything over. So that's going to be 6 over x minus 1 minus 6 over x minus 1 is greater than or equal to 0. And now I've got 3 pieces. They all have different denominators. So my common denominator is going to be what?
X times x minus 1.
Very good. So I need to rewrite each of these 3 pieces with the common denominator x times x minus 1. This piece is missing the x, so I'll multiply him top and bottom by x. This piece is missing the x minus 1, so I'll multiply top and bottom by x minus 1. And this piece is missing both, so I'll multiply here top and bottom by x times x minus 1. That'll give me 6x over x times x minus 1 minus 6x minus 1 over x times x minus 1 minus x times x minus 1 over x times x minus 1. And all of that is still greater than or equal to 0. Now I can write this as a single fraction. 6x minus 6 times x minus 1 minus x times x minus 1 all over x times x minus 1 is greater than or equal to 0. And the places, like I said, the places I've seen people struggle the most is getting through here. So pay careful attention. If you have any questions about how we're doing this, please ask. Don't be shy. Is everybody good with how we got to here?
Yep.
Okay. So my next step is going to be to kind of distribute everything out and combine my like terms. I'll have 6x, and then this is going to be minus 6x plus 6. And this piece will be minus x squared plus x. So what like terms do I have? Well, I've got a positive 6x and a negative 6x. Those go. I got a negative x squared plus x plus 6 left over. All of that is divided by x times x minus 1. And now I need to, the bottom's factored for me already. I need to factor the top though. And I think it might be useful. So let me come over here and factor negative x squared plus x plus 6. I think probably I would pull out a negative because we all like to deal with these things where the coefficient of x squared is positive 1. So that would be negative parentheses x squared minus x minus 6 And then if I factor x squared minus x minus 6, I'm looking for two numbers whose product is -6 and whose sum is -1. That would be -3 and +2. So this negative is this negative. And then this piece factors as x minus 3 times x plus 2. So I get negative x minus 3 times x plus 2 over x times x minus 1 is greater than or equal to 0. So my cut points. Let's see, I've got a -2 from this, 0 from this, 1 from this, and 3 from this. And they're all multiplicity 1. Right, because every one of those factors is just raised to the first power. Which means as we jump over each of them on the number line, we will change sign. So this one will alternate. There's -2, 0, 1, and here's 3. And once I know the sign in any one of these regions, I'll be able to get the sign in all of the other regions using the multiplicity. But we do need to do some amount of work to figure out the sign in one of those regions. I think the easiest place to see this is probably from here. Can anybody tell me the horizontal asymptote for this guy?
Is it -1?
It is, yeah, because that bottom, if you multiply it out, is x squared minus x. So this has HA y equals -1. So in particular, we got to be negative over here. And now because all of these are multiplicity 1, which is odd, we will change sign as we jump over each. So we'll go minus, plus, minus, plus, minus. Now I'm trying to figure out where this thing is greater than or equal to 0. So I'm looking for the regions where we're positive, from -2 to 0, and from 1 to 3. So solution set is -2 to 0, union with 1 to 3. But since this is a greater than or equal to, not a strictly greater than, I do need to worry about the endpoints. So some of these endpoints I can include, some of them I cannot. The endpoints that come from the top, I can include, because when we plug those in here, I get a true statement. So which ones are those? That's the -2 from this guy and the 3 from this guy. So I can put a bracket on the -2 and a bracket on the 3. The 0 and 1 came from downstairs, so they both get parentheses. Not so bad, right? Really not so bad. Once you get through all the algebra, the common denominator and factoring work, once you get to here, this really isn't hard. It can be time consuming if you don't remember the multiplicity trick. And that's why I've been harping on this so hard, right? It's that multiplicity trick is a big deal for graphing. It's a big deal for solving inequalities. It's a big deal for just understanding functions like these in general. So it really is important that you internalize this thing with multiplicities. We used it when we talked about graphing polynomials using multiplicity and end behavior. We talked about it when we graphed rational functions using the multiplicities to get the local behavior near the roots and near the vertical asymptotes. And now we're using multiplicity again to complete our sign charts, our number lines very quickly. Useful all over the place. Now it's just about time to go, right? Let's see, I have you guys till what, 9:15? So the last thing I'd like to do here is just take a quick. Sorry about that, guys. Looks like my internet cut out and cut back in for a second. So we wrapped up here, right? We found our cut points. We noticed they were all multiplicity 1. We used the horizontal asymptote to get the sign over here. And then since each one of these things is multiplicity 1, we know we're going to change sign every time we jump over one of those features. The regions where this function was positive were from -2 to 0 and from 1 to 3. So we wrote this down. And to get the brackets in parentheses, we just noticed that the -2 and the 3 came from the top. So we can include those. The 0 and the 1 came from the bottom, so we cannot include those. All right,
Not sure about anyone else, but I can't see your screen.
Oh, shit. All right, sorry. Here you go. Okay. So this is,
Thank you.
right? Yeah, so we found our solution set by noting where this function was positive from -2 to 0 and from 1 to 3. And then we said, when it comes to the endpoints, since this is a greater than or equal to, we need to check and see whether each of those endpoints satisfies the inequality or not. The endpoints that came from the top do satisfy the inequality because that makes the whole thing 0. So we put a bracket on -2 and we put a bracket on +3. And the endpoints that came from the bottom make this whole thing undefined. If I plug 0 in here, I get something undefined because the bottom is 0. If I plug 1 in here, the bottom is 0 again. So we included -2 and +3 with brackets, and we excluded 0 and 1 with parentheses. The last thing I'd like to do before I let you go is just to take a quick look at the graph of this thing in Desmos. Contextualize some of this. -3 times x plus 2 over x minus 1. Yeah, all right. Well, something isn't right here. What are you doing, Desmos? It's behaving like this is a multiplicity 2 thing, but it's not. Oh, no, there it is. Okay, it's just scaled weirdly. All right. Let me change my Y scale here. There we go. Okay. So here's our graph. And we were looking for places where this function is positive, right? We said this function is positive from -2 to 0, including -2, and from 1 to 3, including 3. So from -2 to 0, where is that? That's here. And if you zoom in, you'll see that, yeah, at -2, this thing goes from being negative, right here, these are negative values, to positive, right here, these y values are positive. So from -2 to 0, and then we cannot include 0 because that's a vertical asymptote. And also from 1 over 2, 3. And at 3, we cross the x-axis again, and these values go from positive to negative. So this solution set does make sense, right? It's consistent with the graph. Really, when you're solving these inequalities, it's very similar to graphing the function. It's very similar. We just don't go through the process of drawing the graph, but you're finding the x-intercepts and the vertical asymptotes. Those are your cut points. And then often we find the horizontal asymptote to get ourselves started over here. The only thing that we're not doing is drawing the graph. But it is consistent with the graph. There was a question in the chat there that I want to address. We're asking, will you specifically list you to find the cut points in the solution set, or the problem to say solve the inequality, and you should know these steps. Yeah, the problem is going to say solve this inequality. So the problem, just like this example says, let's just solve the inequality. On the test, the problem will say the same thing. So that you do need to know the steps.
Since we have a minute, can I go back to it's two problems back, the x minus 1 squared over x plus 1 times x plus 2. I'm so sorry.
No, don't be sorry. Yeah, here we go.
The solution set, if it's all greater than 0, why isn't the negative infinity to negative 2 included?
Oh, it should be. Yeah.
Oh,
I made
okay.
a
I was
mistake.
so
I'm
confused.
sorry. No, you're 100% right. You're 100%
Thank you.
negative infinity to negative 2 should be included here. Yep. Yes, indeed. Thank you. Thank you. Yeah, this region, and this region.
Thank you so much.
Of course. Yeah, I'm so sorry.
Wait, could you go over the next solution set, like the problem right under it?
Sure. So here we were looking to see where is this function negative. And we found our cut points and their multiplicities. We plotted our number line. And to get started, we tested x equals 2 because the horizontal asymptote here was 0. There is no y-intercept that I can use to get started with. So I had to actually test a point to get one of these regions. So I chose to test x equals 2 out here. When we plug 2 in, I get 25 over 72, which is positive. So I write a plus here. And then I use the multiplicities to fill out everything else. So the 1 was an odd multiplicity, so we changed sign from plus to minus. The 0 was an odd multiplicity, so we changed sign from minus back to plus. And then the remaining two, the negative 3 and negative 1, were both even multiplicities, so we don't change sign as we hop over them. That means that the only region here where this function is negative is from 0 to 1. So my solution set was the interval from 0 to 1. Now this was a strict inequality. This was a less than, not less than or equal to. If this was a less than or equal to, I would include the 1. I would use a bracket here. But because it's a strictly less than 0, I'm only looking for places where this function is negative, not equal to 0. So at x equals 1, this function would be equal to 0. So if this was a less than or equal to, I would put a bracket here. But since it's not, we use parens on both sides. Feeling good?
Yeah, that's good. Thank you.
Good. Okay. So we've got plenty of stuff to be working on in WebAssign. There's the second homework for the rational inequalities that is up. And I'm going to be posting a quiz for you. I don't think your quiz is up just yet, but I will be posting that a little bit later today. So be aware. Let's see, actually, I haven't posted you guys' second part. So I'll go ahead and post that last homework and that last quiz today. And then those are the last few things you need to do before the test. If you're looking for extra practice, you can, after finishing those, take a look in the textbook. There is a review for chapter 3. And thankfully, this test is straight up just chapter 3, right? So there's nothing else that you need to sneak around in the book looking for. So if you are looking for extra practice beyond the homeworks and the quizzes, you can take a look at the chapter review in the book. Last time, I think I scanned that and posted it for you. I'd be happy to do that this time as well. Test is Monday. Yeah, exam 2 is Monday. And just like last time, you can take it with me here in person. You can take it with me here online. If you're going to take it online, you need to have your phone set up with Zoom and you need to have your computer ready to use honor lock. If you don't want to deal with any of that stuff, you can take it at the testing center. I will make a walk-in testing reservation for you guys, so you don't need to email me individually if you want to go to the testing center. I'll just set it up so you guys can show up there anytime in the day. Any other questions about exam procedures or stuff like that? Alrighty then, I am going to go ahead and end the meeting here. I have an office hour this afternoon from 1 to 2 p.m. If you guys want to come by and ask any questions, talk about anything, There's another office hour on Friday between now and the test, and those are the last 2 office hours. So if there's anything you're kind of stuck on, you want to talk through or work on together, I'd be happy to do it there. Of course, as always, you can message me on Canvas or ask the 1140 cohort anything you'd like on Discord. But remember, yep, test 2, Monday. If you're going to take it online, you got to come here with Zoom on your phone and also be ready to use HonorLock on your computer. Or you can go to the testing center on the Northwest Campus, Building N upstairs, 2nd floor of Building N. That's it.
I have a
If there's anything else you want to talk about, reach out. Yeah, go ahead.
Well, it's not a question about the test, but I was trying to get into WebAssign, but I'm not able to. It keeps saying error. I mean, everyone can leave. Yeah, it's just
Sometimes WebAssign goes down. So every now and then they have some technical problems. Is this something that's been happening like a lot or just
no,
recently?
it just started this morning, so I wasn't able to finish some of my assignments and a
Okay.
little bit last night. So I'm not sure.
That's okay. If you could, when you are able to get back in, just submit an extension request for those assignments and I'll clear them. Looks like I cleared out everything yesterday and I've got 46 fresh ones since then. So it's normal. I'll go through here and clear all these out in a little bit. So if you could just get back in there and anything you need extended, just click the little request an extension link and that'll send me a message and I'll go ahead and get that sorted out.
Well, I'm going into it now, so just wait until it works. I'm not sure. It's not working now, so.
Yeah, unfortunately, we're gonna have to wait till you can get in there. You can try clearing out your browser's cache or using a different browser. Sometimes those sort of things can cause trouble. WebAssign is loading for me, so it doesn't look like they're having any server issues right now. So I would definitely try clearing out the browser cache.
Okay.
Something like that. But yeah, once you're able to get in, go ahead and request an extension and I'll grant them a little later this afternoon as I'm getting ready for my office hour.
Thank you.
Alrighty, gang, I gotta get moving to another class. I hope you guys have a lovely rest of your day. If you do want help with anything, again, come by the office hour either this afternoon or Friday. That's it from me. I'll see you next time.